Question 9a, part 1. We're given this g of x is equal to 6x to the power of 4 plus 5 for all real values of x, and we need to explain why g is a function but does not have an inverse. Well, g of x is a function because each x value is mapped to a unique value in the range of g of x, but g inverse of x is many to 1, and hence it is not a function. So let's just first write that down. So let's just look at an example of what that means then. It means if we're in the domain of g of x, so say this is the domain, and we have the numbers, say, -1 and 1. Well, -1 to the power of 4 is just going to be the same as 1 to the power of 4. So when we put that into the range of g of x, well, -1 is going to give a value of 11, and 1 is going to give a value of 11. So each of these x's in the domain of g of x, they give us a unique value in the range. So in this case it is 11. But if we're going the other way, so the inverse, that means this part here then is now our domain. But if we have this 11 in our domain, well, that would get put to two values in the range. It could be -1 or it could be 1. So therefore, the g inverse of x does not exist. Okay, so that is part 1. For part 2, we need to find g2 of x and state its domain. So we're trying to find g of x. So it's going to be equal to, well, wherever we see x in our original function up here, g of x, then we're going to replace it with that whole expression, 6x to the power of 4 plus 5. So that means then we're going to get 6 times 6x to the power of 4 plus 5, all to the power of 4, and then plus 5. And this is valid for all real values of x. So we write then the domain is all real values of x. Okay, and that is part 2. For part 3, we're given that h of x is equal to 6x to the power of 4 plus 5 for x less than or equal to k, and we need to state the greatest value of k such that h inverse exists. So that means if we have any positive number for k, like say 3, well then if we plug in -3, for example, then we're going to get that same value of h of x. So that means then we can't have any positive numbers for k. So that means the greatest value of k, such that h inverse exists, is going to be 0. So we have k is equal to 0. So that is part 3. Part 4, for this value of k, which we just found is 0, find h inverse of x. So we'll start by writing out our function h, which is equal to 6x to the power of 4 plus 5, and that was for x is less than or equal to k, which we found was 0, so we have for x is less than or equal to 0. So to find the inverse of h, we just look at this equation here, and we want to make x the subject, and then at the end we can swap the x and the h around. So we'll start by taking off 5 from both sides. So we have h minus 5 is equal to 6 times x to the power of 4, and therefore h minus 5 over 6 is equal to x to the power of 4, and therefore x is going to equal plus or minus the 4th root of h minus 5 over 6. But we know that x is less than or equal to 0, so we have x is going to be equal to the -4th root of h minus 5 over 6. So therefore we get x is equal to the -4th root of h minus 5 over 6. And now we just swap the x and the h around. So where we see h here, we're going to write x, and where we see x here, we'll write h inverse of x. So therefore, we're going to have h inverse of x is going to be equal to the negative fourth root of x minus 5 over 6. Okay, so that's question 9a done. Part B, we're given the function p is defined as p of x is equal to 3 times e to the power of x plus 2 for all real x. And for part 1, we need to state the range of p. So to work this out, we'll look at this part here of the function as 3 times e to the power of x and see what is going on there. So if we have very large values of x, well, e to the power of x is also just going to be very large. And as x gets larger and larger, well, so does e to the power of x. So there's no upper bound to our function. But if we have very large negative values of x, so for example, if we had, say, e to the power of negative 100,000, well, this is actually very, very close to 0. So therefore, this part here, this 3 times e to the power of x, is just going to be very close to 0, but not actually ever reach 0. So for our function then, we've got that 3 times e to the power of x, and then we add 2 to it. So as we get very large negative values of x, it's going to get very close to 0, this term here, but then we add 2. So we're always going to be greater than 2. So therefore, our range of p is greater than 2. So that is part 1. For part 2, we need to sketch and label the graphs of y equals p of x and y equals p inverse of x, and state the coordinates of any intersection points with the coordinate axes. So if we look first at y equals p of x, well, we know p is always going to be greater than 2. So we have a horizontal asymptote at p equals 2. So we'll draw that in. So there's our horizontal asymptote drawn there in red at p is equal to 2. And we know if we've got this here, this p of x is equal to 3 times e to the x plus 2, well, it's going to cut the y-axis when x is equal to 0. So when x is equal to 0, we get 3 times e to the power of 0, which is just 3 times 1 plus 2 is equal to 5. So our y-intercept is going to be at p is equal to 5. So now we can sketch our curve. So it's going to look something like this. It's going to be very close to the horizontal asymptote as x gets more and more negative. Then we're going to come up and cut through the y-axis at p is equal to 5, and then it's just going to grow exponentially large. Okay, so that is the graph of y is equal to p of x. Now for y equals p inverse of x, well, that's just going to be a reflection of y equals p of x in that line y equals x. So for y equals p of x, we had a horizontal asymptote at y is equal to 2, or p is equal to 2, and that means then for y equals p inverse of x, we're going to have a vertical asymptote at x equals 2, so we'll draw that in. So there's our vertical asymptote drawn there in the magenta color. And for y equals p of x, well, our y-intercept was at 0, 5, so that means for y equals p inverse of x, our x-intercept is going to be at when x is equal to 5. So say that's going to be about there, and now we can sketch our curve. So we're going to come up very close to the vertical asymptote to start with, and then we're going to get larger and larger, cut the x-axis at x equals to 5, and then grow exponentially large. Okay, so that's our sketch then of y equals p inverse of x. So we'll mark that in, so that's y is equal to p inverse of x, and we'll just make it clear of where it cuts the coordinate axis. So that coordinate here is going to be 5, 0, and up here for y equals p of x, I'll just mark it in blue, we're going to have 0, 5. Okay, so that is part 2. For part 3, it says, hence explain why the equation p of x equals p inverse of x has no solutions. So looking at our sketch of those curves there, we can see that they don't intersect. So all we need to say is the graphs do not intersect, therefore there are no solutions. So we'll write that in. And that finishes off question 9.